Now we turn to the lab exercises. Time to build and run this chapter's traversals yourself in C. Lab 1 takes about 20 minutes. The goal is to implement breadth first search and print the distance from a given source to every vertex. Write this function in C. It is called BFS distance. It takes the graph, a source vertex, and a dist array that you fill in. Use source vertex 2. You should expect dist to equal 1, 2, 0, 1, 1, 2 for vertices 0 through 5. And remember the key tip. Mark a vertex visited the moment it is added to the queue, not when it is taken off. This is the chapter's main bug in reverse. Pause the video and give it a try. Here is one clean solution. BFS distance takes the graph, a source, and the dist array it fills in. Note it does not need a parent array because the lab only asks for distances. The queue is an array with a head and a tail index. This loop sets every distance to -1, which means not reached. Then the source. We mark visited at source right here at in queue time exactly as the tip warned. Its distance is 0. And we enqueue it. Then we drain the queue, while the head is behind the tail. We dequeue into U. We scan use neighbor list until the null marker. If a neighbor V is unvisited, we mark it visited at once. Set its distance to 1 more than U's. And enqueue it. That is the whole algorithm with the mark in the right place. Here is the run from source 2. Vertex 0 is at distance 1, since 2 is adjacent to 0. Vertex 1 is at distance 2, reach through 0 or through 3. Vertex 2 itself is at distance 0, the source. Vertices 3 and 4 are both at distance 1, direct neighbors of 2. And vertex 5 is at distance 2. That matches the expected array the lab gave you, and all the asserts pass. Lab 2 takes about 25 minutes. The goal is to implement depth first search both ways, recursive and iterative, on the same graph. Then confirm they produce the same visit order. Write both of these functions in C. One does a recursive depth first order. The other does an iterative depth first order. Both fill an order array and report how many vertices they visited. Use source vertex 0. Both versions should report the order 0, 1, 3, 2, 4, 5. One tip for the iterative version: push each vertex's neighbors in reverse order. Without that, its visit order will not match the recursive one. Pause here and try both. Let's look at the solution for Lab 2. This slide shows the recursive version. Reveal it when you are ready. The helper function does the real work. It takes the graph, the current vertex U, the visited array, the order array, and a pointer N that counts how many vertices we have recorded. The very first thing we do is mark U visited. We mark it the moment we arrive, just like in breadth first search. Then we record U in the order array and increase the count by 1. This is where the visit order is built. Now we loop over the neighbors of U. For each neighbor V that is not yet visited, we call the helper on V. That recursive call is what goes deep before it comes back. The active chain of calls is exactly the current path in the graph. The public function just sets up a fresh visited array and a count of 0, then starts the recursion from the source. It reports the total in and out. Here is the run. The recursive DFS order is 0, 1, 3, 2, 4, 5. And the iterative order is exactly the same. The program confirms they match. That is the reverse push trick paying off. An explicit stack reverses the order you push, so pushing the neighbors backwards makes the smallest one pop first, just as the recursion visits it first. Lab 3 is the challenge, about 30 minutes. The goal is to detect a cycle in a directed graph. You will use depth first search with a 3-state color, white, gray, and black. A single visited flag is not enough here. Write this function in C. It is called hasCycle. It returns 1 if any directed cycle exists, and 0 if there is none. Test it on 2 graphs. Graph A has edges 0 to 1, 1 to 2, 2 to 0, and 3 to 4, so it has a cycle. Graph B is the same but without 2 to 0, so it has no cycle. The key idea in the tip: an edge back to a gray vertex, one still on the current path, is a cycle. An edge to a black vertex, one that is already finished, is harmless. That is why a directed graph needs more than a single visited bit. Pause and give it a try. Here is the recursive worker. It takes the directed graph, a vertex U, and the color array. First we color U gray. Gray means U is on the active path right now, discovered but not yet finished. Then we scan U's outedges. Here is the whole point of the 3 colors. If a neighbor is gray, it is an ancestor still on our path, so this edge runs backwards into the path. That is a cycle. So we return 1. If a neighbor is white, it is untouched, so we recurse into it. If that call finds a cycle, we pass the one straight back up. And when every ousedge is done, we color U black. Black means U and everything below it are finished. An edge to a black vertex is harmless. It is a different branch, already closed, not an ancestor. And here is the driver. hasCycle takes the whole graph. First it colors every vertex white. Then it starts a walk from every white vertex. That second loop matters. A directed graph may not be reachable from any single source, so one call from vertex 0 is not enough. If any of those walks reports a cycle, we return 1. And if none does, we return 0. Graph A has 0 to 1 to 2 and back to 0, plus 3 to 4. The answer is yes, there is a cycle. Graph B is the same minus that back edge, so the answer is no. And notice the 3-4 component in both. The second loop is what makes sure it is visited at all. That wraps up graph traversal. Nice work, and I will see you in the next chapter.